Hello, and welcome to the electrical system lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: electric power description and types, 737NG electrical system overview, AC electric buses, DC electric buses, DC power sources, AC power generation, standby electric power system, electric system control panels and indicators, and a lesson summary. In general, electric systems may have interfaces and schematics that are very hard to understand at first. For this reason, we're going to discuss the 737NG electric system in a basic way, so that essential elements can be easily understood and non-essentials can be left out. When in doubt, always refer to the PMDG 737NG Flight Crew Operations Manual or simply leave a message in the comments section of this video. Electricity is the presence of an electric charge that flows within a circuit when excited in order to produce energy. Subatomic particles, known as electrons, are the ones that flow inside a circuit. When this occurs, a little magnetic interaction also takes place. This magnetic interaction is known as a charge. For example, electrons are charged negatively. However, a stable atom has an equivalent amount of protons that are charged positively within the nucleus of the atom. When an atom is excited, it may either lose or gain electrons in an attempt to restabilize itself, thus producing a positive or a negative charge. When charges move around the circuit, they are known as currents. There are two types of electric currents: direct current, DC, where electricity flows in one direction; alternating current, or AC, where electricity flows in two alternating directions. Direct current causes electron flow in one direction by a magnetic field near an electricity conductor. However, it can carry only a fixed amount of energy and usually loses it as and when the current travels a distance. In contrast, alternating current does not lose energy and it can carry a significantly higher amount of power. A variable magnetic force is used to achieve alternating current. DC output energy per charge, or voltage, is constant, whereas AC voltage may be transformed into different values. AC current's output power versus voltage are measured in a unit called volt-ampere, generally expressed as thousands or kVA. Another important concept associated to AC current is the frequency at which the current alternates direction. Frequency is measured in hertz. For example, a 60 hertz frequency is equal to 60 current direction changes per second. Let's now talk a bit about the 737NG electrical system architecture. The electrical power system generates, supplies, and controls electricity for various components in the 737NG that rely on it. Most elements and components aboard the aircraft rely on electricity, either directly or indirectly, for their operation. A few of these are flight deck avionics and display units, landing gear motor, trailing edge and leading edge devices retraction extension actuators, aircraft lighting, and other elements. For this reason, overall redundancy and safety built into the electrical system is considerably high, as many essential components depend on it. We'll discuss this idea progressively as we move through the lesson. Both AC and DC currents are generated and supplied for the respective aircraft systems via wires and cables that conduct electricity. These wires are insulated to protect from contact between two different sets of cables. It's extremely important to keep cables metallically isolated from each other with insulation. Failure to do so may cause short circuits or other weird effects. If you don't believe us, ask Ms. Susanna Darcy, a veteran Boeing test pilot who was once testing a 737NG. Whenever she would turn the aircraft electric power on, she and her test team would notice that all the flushes in the lavatories would activate. This was due to some form of interference between electric cables. The entire electric system has both manual and automatic controls, as well as standby AC and DC systems to provide an emergency source of power. We must also be familiar with the concept of an electric bus. Buses are essentially electric platforms from which electricity is both supplied to and drawn from by the respective aircraft systems. Each electric current type has a respective set of buses for both essential and non-essential items. The whole purpose of buses is to allow essential items to still remain powered if there was an electric power shortage or emergency. During an electrical emergency, it is far more important to have an active, functional communication radio as opposed to having functional strobe lights. For this purpose, both items draw current from different electrical buses. The 737NG uses both AC power from engine-driven generators and DC power that's stored in a main battery and an auxiliary battery. Before having a deeper look at where the 737NG gets its electric power from, let's talk about the available electric buses on it. The AC electric system has two primary buses that take all the generated AC power and divide them amongst smaller AC buses. AC current is supplied as 115-200 volt 400 Hz power. The two primary AC buses are known as AC transfer buses 1 and 2. AC transfer bus 1 subdivides into the following buses: AC main bus 1, AC ground service bus 1, galley bus C and D, AC standby bus. The AC transfer bus 1 also supplies electrical energy to the DC bus 1 through a component known as a transformer rectifier. We'll discuss AC to DC energy transformation and DC buses later in this lesson. Similarly, AC transfer bus 2 also subdivides into the following buses: AC main bus 2, AC ground service bus 2, galley bus A and B. AC transfer bus 2 also supplies energy to the DC bus 2 with another transformer rectifier. Notice that the AC standby bus is partly AC powered only by AC transfer bus 1, but it also has a part which is powered by AC current derived from the DC electric system. DC to AC conversion is achieved with an inverter and will also be discussed later on. Moving on, the DC current system supplies and controls 28-volt power. It's comprised of the following items: DC bus 1, DC bus 2, battery bus, hot battery bus. The DC system has the following power sources: 28-volt battery, battery charger, transformer rectifier units, or TRUs. We mentioned the TRUs before, so let's explain them now. The 737NG has three of these components, which essentially transform and rectify the 115-volt AC power to unregulated 28-volt DC power for the DC buses. The three transformer rectifiers are connected in parallel, which means if one of them fails, the other two may give backup. The TRUs are connected according to the following logic. TRU-1 gets power from the AC transfer bus 1 and connects directly to the DC bus 1. TRU-2 gets power from the AC transfer bus 2 and connects directly to the DC bus 2. TRU-3 gets power from the AC transfer bus 2 and provides a power source for the battery bus. If power from the AC transfer bus 2 is lost, AC transfer bus 1 may supply backup power to TRU-3 through a relay. The DC system has two batteries, one main battery and one auxiliary battery. Both batteries are 48 ampere and 24-volt DC power sources. In very simple terms, the battery's connection logic is the following. The main battery normally only supplies power for APU starting, but is a standby power source when all other power sources are inoperative, such as during a complete loss of AC power if both engines are shut down in flight. We all know that the chances of this occurring are minimal. However, the redundancy must still be built in to make the systems more reliable and dependable. Both batteries are always kept at maximum charge by a main and auxiliary battery charger, powered by the AC power system. In case the batteries were ever to drain on ground, it takes nearly 3 hours to charge the batteries from zero charge to an operational level. It's important to note that the main and auxiliary battery chargers do not charge the batteries when any of the following take place. The aircraft is being refueled and fuel station door is open. APU is being started. Standby power is being used due to a loss of power in the DC bus 1 and AC transfer bus 1, or the main or auxiliary batteries are overheated. As we mentioned, the main battery supplies power for APU start and normal operation of the DC buses. When fully charged, the batteries are guaranteed to supply 60 minutes of standby AC and DC power in case there were AC or DC supply failures. Within DC power, there's also a hot battery bus. This DC bus is always powered and active and is in charge of maintaining energy for two main items: all the fire extinguishing systems and the captain's clock. The hot battery bus, similar to the battery bus, is powered by 28-volt DC power from the battery. All these concepts may seem a bit intimidating at first. The AC system, which we'll discuss now, may be even more complex than the DC system. However, everything will make more sense once we get to the end of the lesson and talk about the interfaces and indicators associated to the 737NG electrical system. AC power in the 737NG is generated and supplied from 4 independent sources: left engine-driven generator, right engine-driven generator, APU starter generator, and external power. The AC system is designed to prevent any two sources from powering a same transfer bus at the same time. If any AC power source is being overloaded, the system automatically removes electrical load from it and channels it to another AC source. This feature is known as load shed. The output power of the 4 AC sources is considerably larger than DC sources, which is why the 737NG electrical architecture is designed so that AC sources also supply energy to DC buses via the transformer rectifiers. Even though both AC transfer buses are powered by separate power sources, a bus power control unit allows for the left and right systems to connect to each other in case there is AC power loss to either transfer bus, ground external power is the only AC power source, or APU power is the only AC power source. All AC power sources supply 115 200-volt 400 Hz power. The external ground power is rated at 90 kilovolt ampere, or kVA. The engine-driven generators are also rated at 90 kVA. The APU electric power supply is dependent on flight altitude. At or below 32,000 feet, the APU supplies 90 kVA power. However, above 32,000 feet, the APU generator supplies less power and it decreases linearly as the aircraft climbs higher. At 41,000 feet, the APU supplied power may be as low as 66 kVA. Let's talk a bit more about the primary source of electrical power on the 737NG, the engine-driven generators. There are 2 generator drives, one for each engine. The generator drives are the normal source of AC power. If they were to fail, the APU and ground power may be used. Each generator drive has the following relevant components: an integrated drive generator, or IDG, and an IDG air-oil cooler. As is mentioned in the 737NG engines and power plant lesson, the high-pressure shaft turns the N2 rotor, which also powers the integrated drive generator through the engine accessory gearbox. Because engine speed is variable, the gearbox speed is also variable. The IDG takes this variable input speed and converts it into a constant 24,000 RPM for the internal AC generator to produce power. The objective of this is to provide a uniform electric supply during all phases of flight, rather than having the cabin lights dim down when engine power is reduced to commence a descent. Each IDG has a constant speed drive section and a generator. Part of the generator drive section is an IDG air-oil cooler that decreases the temperature of IDG oil. Similar to engines, oil is used in the IDG to lubricate and cool down moving parts by minimizing metal-to-metal contact, thus reducing friction. Heat is exchanged between hot IDG oil and cool air from the engine fan. Oil is filtered, pressurized, and ducted towards the coolers at between 240 and 290 psi. If the filter were to get clogged, oil bypasses the filter and flows into the coolers. IDG oil is also in series with the engine fuel oil cooler. This component is thoroughly discussed in the engines and power plant lesson. As we mentioned before, each IDG supplies AC power to its respective AC transfer bus under normal operation. System logic is such that each IDG may also supply AC power to both essential and non-essential electric loads of the opposite AC transfer bus. Moving on, during times when the engines are shut down or faulty, the APU may supply the electric demand of both AC transfer buses. This is guaranteed to work on ground, but during flight, it works only according to the altitude limitations we outlined earlier. Similar to the APU, external ground power may also supply energy to both AC transfer buses. The receptacle is located in the lower right forward fuselage, near the nose gear wheel well. Sometimes during ground operations that involve only cleanups or quick checks, all electric buses don't have to be powered by ground power. For this reason, even though ground power is capable of supplying power to both AC transfer buses, and therefore to all the systems that take power from them, for the purposes of ground servicing, a ground service switch in the forward attendance panel allows for the ground external power to provide energy only to the AC ground service buses. When the AC ground service buses are powered, the following items are available: utility outlets, cabin lighting, and main and auxiliary battery chargers. Note that DC power demanding components are unavailable. To override the ground service configuration, both AC buses must be powered by some other source of power. We've mentioned many items and components associated to the electrical system on the 737NG. What would happen if all primary sources of energy were to fail? Requirements for aircraft certification demand that the aircraft should have alternate and backup sources of power, which need not be unlimited, but should at least keep the aircraft electrically powered for a known period of time. In the 737NG, this system is known as the standby power system. We've already mentioned the word standby a couple of times during this lesson. For example, in the AC buses section, we talked about the AC Transfer Bus 1 powering an AC standby bus. The standby power system provides energy only to essential items in the event that both engines and the APU were unavailable or faulty. The standby produced power is 115-volt AC power and 24-volt DC power. For the most part, we've already talked about the standby system components. However, in order to summarize, they are the following: AC standby bus, DC standby bus, main battery, auxiliary battery, battery bus, hot battery bus, switched hot battery bus, and static inverters. which switch DC to AC power. The standby power system has two modes of operation, normal and alternate. During normal operation, different power sources are provided in case of partial power loss. A complete transfer to battery power is provided if all normal power sources were lost. As we mentioned earlier, the AC standby bus is powered by the AC transfer bus 1. The DC standby bus is powered by 3 transformer rectifiers. The battery is powered by TR3, and the hot battery bus is powered by the battery chargers. During alternate operation, the power sources for standby power are the main and auxiliary batteries. If engine-driven or APU power were lost, both batteries would power the system's standby loads. In alternate operation, the AC standby bus is powered by the static inverters, which convert DC energy from the battery charger and battery bus. Both batteries power the DC standby bus, battery bus, and hot battery bus. For all the contents in the previous sections to make any sense, we'll now talk about all the controls and cockpit indicators that are related to the electrical system on the 737NG. It's important that you grasp these items thoroughly, as these are the components that pilots directly interface with. An electrical interface panel is located within the forward overhead panel. The electrical panel is subdivided into the following panels: AC and DC metering panel, generator drive and standby power panel, ground power panel, and bus switching panel. We'll now talk about each one of these in detail. Let's start with the AC and DC metering panel. The AC and DC metering panel has the following elements. DC meter selector selects a single DC source for DC volts and amperage indication. DC ammeter indicates amperage of the selected DC source. DC voltmeter indicates voltage of the selected DC source. Similarly, there is also an AC meter selector, which selects a single AC source for AC volts, amperage, and frequency indication. AC ammeter indicates amperage of the selected AC source. AC voltmeter indicates voltage of the selected AC source, and an AC frequency meter indicates frequency of the selected AC source. There is a bat switch that has two positions. Off removes power from the hot battery bus and the battery bus when normal power sources are available. Power from the DC standby bus, static inverters, and AC standby bus are also removed when the battery is the only power source. On automatic switching of standby electrical power to battery power is provided when a loss of normal power is detected. The bat on position is guarded. A cabin and utility switch is normally there to either supply or remove electrical power from galleys and cabin equipment systems. When the switch is placed off, the following items lose electrical power: left and right recirculation fans, door area heaters, drain mast heaters, lavatory water heaters, external logo lights, potable water tank compressor, 115-volt AC shaver outlets. Most of these items are not available in the simulator, so you don't really have to memorize them. Just keep in mind that certain passenger cabin and galley systems are lost when the cabin utility switch is placed off. The in-flight entertainment and passenger services switch works with a similar logic to the cabin utility switch, where if the switch is placed off, electrical power to components in the passenger seats and in-flight entertainment systems is removed. Of course, the only purpose of turning both these switches off would be to conserve electrical power in case there was a shortage or unavailability. If the electricity demand is too high, these switches may also be turned off to conserve electrical power for essential aircraft items. There are 3 indicator lights in the AC and DC metering panel. Transformer rectifier unit light. When illuminated on ground, it indicates that any transformer rectifier unit has failed. When illuminated in flight, It indicates that either the TRU1 has failed or the TRU2 and TRU3 have failed. Electrical light. The electrical light illuminates when there is a fault in the DC or standby power systems. Note that this light is only operative on ground. Bat discharge light. The battery discharge light is illuminated when the battery switch is placed in the on position and there's an excessive current discharge from the main battery. Moving on, the generator drive and standby power panel has 2 switches and 2 indicator lights. A disconnect switch disconnects the integrated drive generators when electrical power is available and the related engine start switch is placed in the idle position. The switch is red in color and guarded because after disconnection, the IDGs may not be reconnected during flight unless it becomes imperative for safety reasons. Normally, maintenance personnel would have to perform this reconnection. The other switch in this panel is the standby power switch, which controls the operation logic of the standby electrical system we talked about in the previous section. It has 3 positions. Auto. The normal and alternate modes of operation are engaged according to AC power availability. This position is guarded. For example, when the standby power switch is placed in auto and the AC transfer buses are powered, the AC standby bus is powered by the AC transfer bus 1 under the normal mode. When all AC power is lost, the static inverters under the alternate mode power the AC standby bus. Off. The AC standby bus, DC standby bus, and static inverters are no longer powered, and a standby power off light illuminates above the switch. Battery, or BAT. AC standby bus is powered by the static inverter, and the DC standby bus is powered directly by the battery. The BAT position can be regarded as a manual control when compared to the auto position. Finally, in the generator drive and standby power panel, there is also a drive light that illuminates when there is low oil pressure in the IDG caused by one of the following conditions. IDGs disconnected through the generator drive disconnect switch. IDGs disconnect and trip off due to high IDG oil temperature, IDG failure, or engine shutdown. Moving on, the third electrical panel in the 737NG is the ground power panel and has only 1 switch and 1 light. A ground power switch that is spring-loaded to neutral has the following positions. Off. Disconnects all ground-supplied power from both AC transfer buses. On. Removes any previous connection to the AC transfer buses in order to avoid multiple sources powering the same transfer bus. The on position will only connect ground power to the AC transfer buses if the power quality is the appropriate. Above the ground power switch, a ground power available light illuminates in blue whenever external ground power is connected and the power quality is appropriate enough to power both AC transfer buses. Last but not least is the bus switching panel. This panel has the following switches. A gen switch that is spring-loaded to neutral and has the following positions. On. Connects the IDG to the related AC transfer bus and disconnects any previous power source, like for example, ground power. Off. Disconnects the IDG from the related AC transfer bus. When the related AC transfer bus is not being powered, a gen off bus blue light illuminates. A bus transfer switch is also present and works in a similar logic to the bleed air isolation valve. The isolation valve is covered in the air system's bleed air lesson. This switch has the following positions. Auto. Power is maintained to the AC transfer buses from any source of the AC power sources. DC buses are connected or isolated as per the system logic. Off. AC transfer bus 1 is isolated from the AC transfer bus 2 if only one IDG is supplying AC power to both buses. DC buses are isolated from each other. If there is no manually active AC power source to the related transfer bus, a source off light illuminates. Similarly, if an entire AC transfer bus is not powered, the related transfer bus off light illuminates. A final switch in the bus switching panel is the pair of APU gen switches, which have the following positions. On. When neither AC transfer bus is powered by the IDG, moving a single APU gen switch to on connects both AC transfer buses to the APU generator. Disconnects ground power if it's connected. Opposite side source off light illuminates until its APU gen switch is moved to the on position. When both AC transfer buses are powered by the IDGs, moving a single APU gen switch to on powers the related AC transfer bus from the APU generator. The opposite AC transfer bus still receives power from the IDG. Off. If the APU generator is powering both AC transfer buses, moving a single APU gen switch to off will illuminate the related source off light, but the APU continues to power AC transfer buses. Moving the other APU gen switch to off will disconnect APU power from the AC transfer buses. If the APU generator is powering one AC transfer bus and the IDG is powering the other AC transfer bus, moving the related APU gen switch to off disconnects the APU generator from the AC transfer bus. Therefore, the IDG powers both AC transfer buses. Most large aircraft have very complex electrical systems to meet the requirement of electrical power for all the components. Understanding them thoroughly is desirable but is difficult at first. The 737NG is no exception. We've seen during this lesson that the electrical system has both manual and automatic controls, as well as a fully functional standby electrical system that powers essential items for approximately 60 minutes after an electrical failure. In the handout section of this video, we've included a list of essential items that are powered by the standby system in case of a full electrical failure. Worth mentioning is that the entire electrical system is also protected by circuit breakers located behind the first officer's seat. These circuit breakers jump when there's a problem within the related circuit and may be reset on ground by maintenance personnel. Flight crew may also reset a tripped circuit breaker if it becomes imperative for safety reasons. A cooling time must be allowed within successive circuit breaker resets. Don't despair if you don't understand the electric system very well. Even current 737NG pilots sometimes find it hard to understand the concepts at first glance. However, if you have any doubts, refer to the PMDG 737NG Flight Crew Operations Manual for more information, or simply drop a comment in the comments section of this video. This lesson covered the following topics: electric power description and types, 737NG electrical system overview, AC electric buses, DC electric buses, DC power sources, AC power generation, standby electric power system, electric system control panels and indicators, and a lesson summary. Until next time, throttle on!